Hi everybody. In this video I want to do an example problem involving Newton's second law, kinetic friction, and at the very end a little bit of static friction. So here we go. Imagine we have a 100 kilogram crate that at the instant shown is sliding to the right. Imagine that it's being pulled with a constant pulling force, constant in both magnitude and direction. Imagine the magnitude of this pulling force is 200 newtons and the direction of that is 40 degrees above the horizontal and to the right. Imagine that the coefficient of kinetic friction between the crate and the floor is 0.300 and the coefficient of static friction between the crate and the floor is 0.400. Our job in this problem is to calculate the acceleration of the crate at the instant shown, and also, assuming that this pulling force is constant in both magnitude and direction, to determine what happens. What's the ultimate fate of this crate? All right, so let's get started. Clearly, to get the acceleration, we need to use Newton's second law of motion. Newton's second law of motion says that the sum of the forces acting on some object equals the mass of the object multiplied by the acceleration of the object. So if we want the acceleration of the object, we need the forces acting on the object. Not the forces the object exerts on something else, but the forces that everything else exerts on the object. In order to puzzle out what those are, we want to draw a free body diagram. That is, to draw this object, the 100 kilogram crate, free from everything else so we can show the forces only acting on the crate, because those are what impact its acceleration or determine the acceleration. All right, so let me just draw this box free over here. That's good enough. Doesn't have to be perfect dimension. We identify the forces acting on the crate. Well, I've got the pulling force of magnitude 200 newtons and that direction shown. So let me sketch that in. So there's roughly sketching in 200 Newton magnitude. And then I'll just sketch in this angle above the horizontal, 40.0 degrees. Great, so that's one of the forces. Well, presumably this is happening near the surface of the Earth. The Earth will exert a gravitational force on this crate of magnitude mg, where m is the mass of the crate, 100 kilograms. G is 9.8 meters per second per second. 9.8 times 100 is 980. And the units will come out kilogram meters per second, which is a newton. OK, now, if this was all that was going on, then the downward vertical part of this would overwhelm the upward vertical part of this, and the thing would accelerate downward. But we have a floor here that's preventing that from happening. To prevent this thing from accelerating downward, the floor is going to exert an upward force. There's two kinds of forces between surfaces, or two parts of the force between surfaces. The force that's perpendicular to the interface we call the normal force. So the surface will exert an upward normal force on this crate to keep the crate from sinking into it. And if I was really careful, I could draw those to scale. I'm just going to draw it like that. Look, this is a quasi-scale. All right, the other component of the contact force is the frictional force. Now this is sliding, so we'll be in the realm of kinetic friction. Now, kinetic friction is always opposite the direction of the object's velocity. So if the object is sliding to the right, the kinetic friction force will be to the left. So let me put that in there. And I probably may, well, who knows about the size? We'll get that later. Kinetic friction force. And the magnitude of the kinetic friction force will be the coefficient of kinetic friction, which we're given as 0.3, times the strength of this normal force, the upward part of the contact force that the floor is exerting upward on the crate. Normal, because normal is another word for perpendicular. All right, so you can think of the normal force as the normal to the plane, normal to the surface component of a contact force, and then the frictional force is the in the plane component of the contact force. Great. And that's our free body diagram. So now we're ready to roll, except when we apply Newton's second law, it's usually convenient to apply it in component form. So I should pick a coordinate system, a nice convenient coordinate system that aligns with as many of these arrows as possible, or which is just a convenient choice for me. So I'm going to take the positive x direction to the right, and the positive y direction to be up. That'll be my coordinate system. Then to apply Newton's second law in component form, I need to make sure that all my forces are broken into components along one or the other of those axes. So that's good. That's in the negative y direction. Normal force, that's great. That's in the positive y direction. Frictional force, the negative x direction. But we've got this nonconformer right here. So let's break that up. So I can take this and break it into an x component and a y component. And the x component, well, this x component is adjacent to the 40-degree angle. So I'm going to have magnitude times cosine of the angle for this adjacent side. So 200 newtons times cosine of 40 degrees, really 40.0 degrees, but I'm running out of space. I can grind out that number, and that comes out to 153.2 newtons. All right, so then I've got this one here. I'm going to draw another arrow right there. This is, if I could put this over here, it's opposite to the 40-degree angle, right? So there's a right triangle. The 200 Newton side, that's the hypotenuse, that's the magnitude, the hypotenuse. Here's the adjacent side. This is the opposite side. Opposite goes with sine. So I have 200 newtons times the sine of 40 degrees. Again, 40.0, just being sloppy and giving myself some extra space. If I multiply that out, that's 128.6 newtons. All right, so this is just rewriting that. Great. All right, and that's as far as we can go. We know what mu sub k is. That's 0.3. I guess I could preliminarily put that in there, 0.300. But I need to know F sub n. And I need to know this frictional force. All right, the acceleration is going to be entirely on the x-axis, not at all on the y-axis. And to see why that's the case, let's go back to our discussion of when we talked about the normal force. So imagine there was no surface here at all. All we would have vertically would be the downward gravitational force and this upward component of the pulling force. Clearly this will outweigh this, and so the thing would accelerate downward in the absence of a floor. But the floor prevents that from happening. The floor keeps it from accelerating downward. This is not enough to accelerate the crate upward, but the floor prevents the crate from accelerating downward. So this normal force will be as big as it has to be to exactly make this acceleration in the vertical direction 0. And that's the key to figuring out what that normal force is. We can look in the y direction in our Newton's second law and look at the y component of that. So sum of the forces acting on the crate in the y direction equals the mass of the crate times its acceleration in the y direction. As I just noted, that acceleration in the y direction is 0. 100 kilograms times 0 gives me 0. So on the right-hand side of this equation, I'll have 0, and I'll wait to write it out so I see how far it goes. So then on the left-hand side, I need to go to my diagram and look for the forces that are in the y direction. Now, we're applying this in component form. The whole point of that is to make sure that all of our forces have been broken up into components that are either along the x-axis or the y-axis and nothing else in between. All right? So this is in the negative x direction. This is in the positive x direction. They have nothing to do with the y direction. This and this have nothing in the y-axis. The only y-axis things we have are the downward gravitational force, the upward normal force, and this upward component of the pulling force. So let's plug those in. In our coordinate system, up is the positive y direction. Let's do that one first. I've got this one upwards, so that'll be positive. So I've got 128.6 newtons in the positive y direction. I have F sub n in the positive y direction, plus F sub n. And I'm assuming when I label these things, I'm putting a positive amount on there, and then the arrow gives me whether, the arrow allows me to interpret whether I want to put a positive or negative sign. the magnitude of this arrow is 980 newtons, but it's in the downward direction, the negative y direction. So I have plus a negative 980 newtons, or just minus 980 newtons. Down on the right-hand side, I got 100 kilograms times 0, which gives me 0. If I solve for the normal force magnitude, which is what I've got there, I'd have a positive 980 minus 128.6, both in newtons, and I get 851.4 newtons, keeping an extra figure now because we're going to use this intermediately. Once we've done that, we can plug that in. In fact, let me do that here. Take this, plug that right in for our F sub n. And now we can figure out what the frictional force magnitude will be. We'll take 0.300 times 851.4 newtons, and we get that F sub k will equal 255.4 newtons. Great. So now we can turn our attention to the x direction. We know there's no component of the acceleration in the y direction, but there will be a component in the x direction. We only have two x component things. We've got this, 255.4 newtons to the left and 153.2 newtons to the right. Clearly this is going to outweigh this, so the acceleration will be to the left. In our coordinate system, that means the acceleration should come out negative. Sorry, the x component of the acceleration should come out negative. So let's see what happens. I'll put this in green. So sum of the forces in the x direction acting on the crate equals the mass of the crate times its acceleration in the x direction. This acceleration will not be 0. This acceleration component is what we're trying to find. So we go to our diagram, look for our components. We only have two components along the x direction, this one and this one. We have positive 153.2 newtons. That's the x component of the pulling force. And we have 255.4 newtons in the negative x direction. So I can go plus a negative of this, or just write minus 255.4 newtons equals 100 kilograms a sub x. Subtracting this from this gives me just over negative, a little bit more, something a little bit more negative than negative 102. Dividing by the 100 kilograms, I can solve for a sub x. And I'll leave those details for you. You can do those steps. And I'll write the answer. I get minus 1.02 meters per second for the x component of the acceleration. Now I can go ahead and box that, but I should really interpret that. This only means something with a coordinate system next to it. The units, newtons, are kilograms times meter per second. Divide the kilograms by kilograms, we're just left with meters per second for a sub x. All right, so what does this mean? Well, the positive x direction is to the right. We have a negative sign for our x component of the acceleration. So that means the crate is accelerating to the left. So it was sliding to the right, but it's accelerating to the left. That means it's slowing down. So let me put that in two pieces. If I want to write this as a vector, I'll write a vector. I could write something like this, for example, 1.02 meters per second of magnitude, and then direction, like a little arrow, or I could say to the left. Both of those things will clearly give the magnitude and direction of the acceleration. Or if I want to rigorously hold to this coordinate system, I could write that a is equal to minus 1.02 meters per second times the unit vector I, for example. Okay, so this leads to our last question. If this pulling force is constant, which means if all these conditions are the same, like this force isn't going to change, right? That's the gravitational force. That depends only on the mass of the box and the acceleration g due to gravity, which is not changing near the surface of the Earth. If this isn't changing, then nothing else is going to be changing in this problem. Well, I shouldn't say nothing else is going to be changing. No other forces will be changing. Nothing in our geometry of our forces will be changing. So, assuming that the pulling force stays the same, then neither this nor this will change, and the acceleration will continue at 1.02 meters per second to the left. So let's imagine if this object was sliding to the right with some velocity. Say it was sliding to the right at, I don't know, just imagine, 5 meters per second. Well, it loses 1 meter per second, roughly, per second of velocity. So each second, its rightward velocity will change by about 1 meter per second to the left. So if it were originally traveling, just as an example, approximately at 5 meters per second to the right, after one more second, it would be traveling at 4 meters per second to the right, then 3 meters per second to the right, then 2 meters per second. And I'm rounding this, right? This is approximately 1 meter per second per second. All right, so if it were originally traveling at 5 meters per second to the right, and it might not have been, but if it were, in about 5 seconds, the thing would come to rest. And if it were traveling faster, it would take it longer to come to rest. If we're originally traveling at 2 meters per second, it would take about 2 seconds for it to come to rest. Great. The question is, what happens after it comes to rest? Well, once it comes to rest, you might think, wow, gee, now then it's going to start accelerating this way because this force outweighs that. But wait, it only has this when it's sliding. And furthermore, the sliding friction force is never in the direction of the velocity. If the thing were to somehow start sliding to the left, the frictional force, the sliding frictional force would be to the right. And friction doesn't work that way. You don't have something sliding to rest, and because it's slowed down, it suddenly starts taking off in the other direction. Wouldn't make any sense. All right, so what happens once it becomes to rest? It's in the static situation. So what we should do is we should figure out the static friction situation. So let me rewrite this here. I'm going to put this here. So once it becomes to at rest, we'll have static friction. And static friction has this less than or equal sign, which makes it a little more complicated. So static frictional force will be less than or equal to 0.400 times this normal force magnitude, which we calculated up here as 851.4 newtons. If you multiply that out, you get 341 newtons. So the static frictional force has a magnitude less than or equal to 341 newtons. Okay, now we need to attack this less than or equal to thing. It says less than or equal to because it's only as big as it needs to be to keep the object at rest. We're pulling to the right here. We've got up and to the right with 200 newtons, but the rightward portion of that is 153.2 newtons. So the static frictional force will not be the full 341 newtons. It only needs 153.2 newtons to the left to completely block this out and keep the thing at rest. The ground under these conditions with this normal force, or I should say the floor under these conditions with this normal force could exert up to 341 newtons of static friction. But it can't exert more than this. Static friction is not going to cause this thing to start accelerating to the left. In the static case, so what will happen is, if this thing came to rest and then we are to ramp the force up, maybe keep this vertical component the same, but then change the orientation of the force and the amount to just tick this up higher and higher and higher. If this horizontal component ever exceeded 341 newtons, again, assuming we're not changing this vertical component because that would play on this and change everything else. So imagine somehow that we pull harder, but we change the angle so that this part stays the same, but this part gets bigger and bigger. If this part ever got bigger than 341 newtons, then this thing would pull again to the right because this would overcome the 341 newtons of maximum possible static friction. But we don't have that. We only have 153.2 newtons. So once this thing comes to rest, there'll be a static frictional force not of this amount. It'll be less than or equal to this. but it will be equal to 153.2 newtons to the left. That is, once the thing is at rest and then no longer accelerating, this will just balance that. So the ultimate fate of the crate will be, if it's sliding to the right and if this force doesn't change, it'll come to rest, and then once it's at rest, the static frictional force will apply just enough to the left to balance out this horizontal component of the pulling force to the right. And so the static frictional force will be 153.2 newtons to the left to prevent any acceleration. All right, so I hope that's helpful. That's all I want to present with this video. Thanks for watching, and I'll see you next time.